Hello, everyone. I'm sure you are doing extremely well. So, till now, in the earlier part of this video series, we have already covered the basics of memory hierarchy in our previous videos, and we have covered various concepts like SRAM, DRAM, and the concepts of cache and how all of them come together internally to make a sub-millisecond latency system. However, today we will go real deep or much deeper into the same concepts of the memory hierarchy. What we will try to cover is we will see how why GPU is faster than CPU. It is a very important concept in the LLM world, and also our concepts will get cleared in this process when we try to understand the differences of architecture between CPU and GPU. And also we will take systems like Google search. We will try to see how it uses the every bit of performance in an operating system to make the search in a sub-millisecond in a sub-millisecond processing. It gets returned to our browser, how it works internally and how it uses every bit of the OS performance. Okay, and then we will also come into the real core of the memory architecture, like where the fetch, decode, execute, and the write, those hierarchical things are happening. Like probably anybody who has ever studied the Calvin book, you might have seen that fetch, decode, execute, write. These are one of the very important CPU cycles for every single instruction that is being executed. So we will take very deep dive into it. Okay, so now let's go into our um, let's move on to the concepts of CPU and GPU. Okay, so one of the few one of the phenomenon of the modern time uh, is it is the rise of the GPU with LLM. Okay, so in the modern system design, we always see uh, under the hood the LLMs when they are being trained and when they are returning our queries. You might always heard about like how exactly the companies like Nvidia and the other GPU companies, like some of the Chinese companies, are literally fighting for the market right now. So when the actual LLM or the model building is an exercise, it is totally built upon the operating system concepts of the GPUs. So that is why understanding GPU in modern times is very important. So what we are going to do is we are going to do a some deep dive around it, and we will try to understand why GPU is faster than CPU on a very high level. Okay, so on a very high level, if you have to understand CPU, it has a very few core who can perform powerful operations. Okay, and whereas GPU, it has thousands of small cores. Okay, so it can be thousands or even it can be more, thousands of small cores with massive parallelism support. With massive parallelism support, uh, it will we will come into the point of the parallelism, like how parallelism is being done and how fetch, decode, execute, write, all these things comes into picture. Okay, so a GPU, when we are thinking about let's take a real world example, like how LLMs are getting trained and how chat GPT or any GPT based system returns our query. Okay, so if we try to understand this real world flow, then probably what exactly is GPU doing behind the scene, it will be kind of way more clear to us. Okay, so what happens? What happens for a LLM is primarily it does a model training. Okay, so during a model training, when we see it mathematically, there is a lot of mathematics happening behind the scene. Okay, and what are those kind of mathematics? There are things like matrix multiplication. Okay, there are things like matrix multiplication that happens behind the scene, and it uh, happens with something like forward and backward pass. So I'm not going into the details of the forward and backward pass, but just understand this LLM training. This LLM training needs like thousands of operations in parallel. Okay, thousands operation in parallel. So what exactly happens is, in case we are using CPU, CPU will be almost 100x slower because we only have around 8 to 64 cores, right? Like, so if we just even see the most powerful CPU these days, they will have like maximum 64 core. So having 1000 parallel operation in 64 cores is again, there is a very high wait time around it. Now when we are talking about GPU, okay, so GPU had this 1000 plus cores, and what it is able to do is it is able to parallelize all the matrix operations and all the propagations. Again, if you do not completely understand what the forward and backward pass, it is totally fine. Probably you might need to go into little deep into the AIML concepts on that, which is not in the scope of this particular video. So I'm not again going into the detail of it, but that is what you can even try to train a model in your CPU. You will see like even a simple model training will take probably like 48 hours, which I myself have tried. But when we are doing it in a GPU where the 1000 plus cores are being done, so there, because of that capabilities parallel compute capabilities, what exactly happens is we get very fast access towards the large tensors, and the latency becomes very the latency become very less, and we get to train our model in a very less time. Okay, and also there are some other implications as well, like while we are working with huge data centers and the models, we get to see a lot of power burning also, like when we are talking about the power burning, the electricity burning also for the CPU based system, whereas GPU actually can handle it in a very efficient manner. It is because of primarily into this multi-core systems, because the more the cores we have, the more parallel execution we can achieve. Okay, so now the next thing is also, suppose we are serving the request, like we are I I'm just making a request in ChatGPT. Okay, just think like this. So what the ChatGPT will be doing is, in that case, it will be serving the request through the model. Suppose like O3 mini. Okay, using O3 mini, GPT is serving the request. So what exactly happens over here is, initially one API call will be made, right? One API call that would go through, and then it is passed through the neural network of the LLM. So when we are talking about the LLM model, it generally passed through the neural network. Okay, and again, like if you do not understand what neural network is, that's totally fine. I'm just putting some information around it so that you have some idea about the complexity that goes behind the scene. Okay, and once it goes through the neural network of the LLM, then what happens is this layer contains like billions of parameters or the weights stores at the matrices, and each layer performs the matrix multiplication between the input tokens and the weights. So internally what happens is there are input tokens are being passed, whatever we enter as an user, and those input tokens are being passed on to our neural network, and then all the matrix multiplication and all the weight calculation happens, and then all the data that, like the output that comes from that, is being put into some kind of a register. Okay, is a some kind of a register or cache when we are talking about our our multimodal chat systems. uh, this is happening on the server end. Okay, so this whole operations are happening around the server end. The input tokens are coming, the output are going into the uh, cache or the registers, and then what happens is it returns the it returns to the user. So here, suppose I haven't mentioned it earlier, suppose here the user is there who is making the server call. The user is making the API call, and this API call then goes into here from the cache register. The data goes back to the user. Okay, this is what exactly happens. Now, also there are few other things you will see, like while we are having a conversational bots. Okay, so for example, conversational bots, what happens there is we will always see that our chat is saved in memory. So that is also one of the very important aspect. This thing is being known as the context window. So our context window also has to be served through our cache. That is the time when the whole neural network will be getting our tokens. Also it will use our context window. Also it will use our context window, and all these things will come together and serve this request back to the user. So with so many requests are coming and this many number of computations are happening, for example here as I was telling, all the weight calculation, the matrix multiplication, the weight calculations, whatever that is happening around. Okay, all all these things has to be done parallelly, and you know, like how many requests people are putting into chat gpt through their window, through their chat window, or through the API calls. All of these are being served from here. Okay, and with so many requests coming and the computational happening in GPU, if at all we are using CPU which have fewer cores, so it won't be able to exploit the massive parallelism which is required to run something like LLM. So anytime we are running any local LLM, just make sure that you have the proper GPU in place. Like suppose there are many open source models are there, and you want to create your own organizational's own organization LLM. So now the problem statement, suppose you have some kind of a localized problem statement within your organization that take any open source model. It can be like something around the, the Facebook models, or like DeepSeek also have open source something. We are using those open source model of the Alibaba or DeepSeek, and using that create LLM for your organization. And the first thing that you will be doing there is like you will select chip system with a great GPU. Okay, because now probably you understand without that parallelism the LLM won't be able to even fine tune, train, or serve this many number of requests, or performing this multiple matrix multiplication which goes behind the scene for to serve a simple requests of API call. Okay, so let's explore how the complete flow would look like for an API request to the LLM, and we will try to formalize it in a little bit more nuanced way than this. Here too we were just doing the rough sketch around it. Okay, so suppose there is a end user. Okay, suppose there is a end user, and this end user is making a post request to the server. So when I say post API call, it can be something like it can be some sort of a prompt. The prompt can be what is um, quantum computing. Okay, something around that. Prompt can be what is quantum computing, and then what it would initially do is it will definitely go to the backend server. Like here, we are not even hitting the LLM at first. We are just going into the API server, and from the API server, probably few other things like the load balancer, um, the things like the rate limiting and other subscription authentication, everything will happen, which I'm not going into the detail at all, because our concentration is mostly around the operating system side. Then it goes through a very interesting layer that is being known as the tokenizer. Okay, so this layer that you see, this is nothing but tokenizer. Okay, so it goes through the API would take the input, and it would go through the tokenizer, and after the tokenizer, what happens is, from the all the tokens, it goes to GPU for the inference. Okay, so now it goes to the GPU. So now you understand, like in our GPU, like where the actual LLM model is there, we do not directly send the query over there. We tokenize it, and the whole token that is there, that is being sent to the GPU. And then in the GPU, what happens is, GPU will go to the VRAM or the global memory. So it goes to the VRAM or global memory, and what it does is, from here it will go and load the model weights. It will load the model weights, and then in this layer only, like I'm not writing all those things in very detail, but all the model weights and everything that comes, they might go into like something like L1. This can be L1 cache, this can be L2 cache. So what happens is, from here it goes to L1, it goes to L2, something like that, keep on happening. Okay, and in that case, suppose there are other context window and my chat memory, everything that comes in play, that can be in some sort of a cache layer. So we can even maintain a global cache sort of a thing. So with the global cache, and with a global cache, it will also take these inputs, and using this all calculations, what happens is, like it generates the token again. So then that token will be put into a normal user understandable format, and then that token is being returned to the end user. So I have introduced this response streamer now. So as you can see, what exactly happening is, once this token comes, using this whole mechanism, like by loading the model weights, by using the context window and doing all the calculations, it keep on generating the token, and these tokens again get decoded. It goes to the response streamers, and then what happens is, this response streamer then return the results to return the results, or like we can call it as a streamed token, because end of the day, LLM, they return token only, it return the stream token to the end user. So you can see over here, the thing that I want to point your attention to, all the things like our VRAM, our global memory, the L1 and L2 cache, even the context window, it can be some kind of a like RAM or custom cache or L3 cache we can put. So all the memory hierarchy that we see over there, that our secondary storage, our traditional disk, our flash disk, our main memory, that is our RAM cache in the registers. Suppose in the registers, like we might want to do uh, some kind of a ALU based calculations, where we are expecting the CPU to, or our GPU to return some calculations. So all of these things will come in play over there. Okay, the registers, the cache, the main memory, flash disk, traditional disk, as you can see, L2, L3 cache, our RAM, and there can be something in our main data in our main disk also, which our GPU might be using. So all those things comes in play, and then the decoded token are being putting into one of the program that is running on that server is called response streamer, and that response streamer then keep on returning the results one by one to as a stream token. So behind the scene, something like server sent events that are being sent from the response streamer to the end user. So again, coming back to the comparison, had it been CPU serving so many requests, and doing all the matrix multiplication and the load model weight latencies, matrix multiplication and the model weight rendering, I would say, would have taken uh, like a would have taken a very high latency. Okay, so this is for the CPU. So that is why probably we understand that how core um, like how multiple cores in the GPU helps in this process. And not only in the LLMs, there are many other big tech system where this kind of architecture is being used. So now probably we understand that whether it is CPU and GPU, uh, the full memory hierarchy that we have studied earlier, that is being used there also, but probably with the help of multiple cores, we are able to serve the requests with lesser latency. And just a point to note, one of the things that we have been talking over here is about the parallelism. So parallelism is something that we will discuss in the later part of the video in super detail. So just save it for this time, like when multiple request comes, how exactly CPU or GPU using this fetch, decode and execute write and multiple parallelism architecture, it provides responses in a very in a very low latency. Okay, so now let's come into the one of the again important thing, that is RSIC versus CSIC. Okay, so again this is very important in terms of our modern computing. So RSIC is basically reduced instruction set computer, and sorry, it is not RSIC, it is RISC, and it will be CISC. Okay, so RISC is the reduced instruction set computer and CISC is complex instruction set computer, and they are two different approaches for the processor architecture. So the processor that when we are talking about in our CPU, generally either it follows RISC or it follows CISC. Okay, so let's take a real world example of Apple. Okay, so why I'm taking example of Apple, this is one of the most prominent phenomenon of our current time, where Apple has moved from one architecture to another, and they have got massive gain. So initial level, Apple had CISC architecture, okay, that is S60, S86 or 32-bit based system, but later they have moved into RISC. Okay, so what has happened over there is in a in an earlier phase of Apple's development, I think it is around 2006 to 2020. What it was doing is it was following CISC architecture, which is nothing but Intel x86. And then in the meantime, Apple started their own research of making some shift of this architecture. So earlier, uh, x86 has some advantages as well. So it had a very strong compatibility with the existing software, but it was not giving any control on the chip design. So what happened in the Apple is they were not having any control on the chip design. So they decided that in 2020 plus time, uh, they decided that they will move on to the different RISC based architecture, and that brought very famous chips that is being known as like M1, M2, M3, and it is currently going on like I think M4 Pro is also on the market right now. So Apple launched this M1, then M2, and M3 chips based on the RISC architecture or a ARM based architecture. Okay, so now they have fully custom system on chip where they have CPU, GPU, NPU, memory, everything unified, and there are a lot of advantages they have. For example, the first is one of the very hardware from the hardware perspective, you will always see less heating is happening on this kind of chipsets. So there is a thermal management that goes. uh, there is the uh, there is an insane energy efficiency that they have achieved. So in case anybody is using MacBook, you might have seen that that when you have shifted to M1, M2, or M3 from the previous the Intel based models, the battery life has gone really better, and also the single and the multi-core performance. Apple has concentrated on their hardware, and now it has been way better than what it used to be in the CISC or the earlier Intel x86 models. Okay, so why RISC shines now? Because like it now runs in even mobile computing, and it helps in the battery life. It uses the unified memory architecture, which even reduces the latency of its requests, and it gives you better parallelism in the R in the RISC architecture. And now why these things are giving a better parallelism, or why this thermal management and energy efficiency, uh, less latency, I will also write that. Yeah, energy efficiency, less latency, all these things are happening, that we have to go into little internals of it, but I'm not taking it into the scope of this particular video, because that will be a completely different Pandora's box we will open. So I'm not going into that direction right now. So when does shines right now? Let's just understand the use cases. That will be enough for our OS internals logic. So initially in the mobile devices, because we needed like low power and the long battery lives. Even the laptops, because they need best performance of per electrical signal, which RISC provides. Also, all the cloud servers, if you see, they have moved from RISC, from the CISC, other than some like outlier use cases, and also like all the LLMs. Okay, when we are talking about the edge AIML. Edge AIML means like in the cloud when we are doing all the computations, all the LLMs, like the efficiency matrix ops, the NPU accelerations, everything moved on to the RISC architecture. Even the developer power stations, like if you are a developer, I'm sure like you can just check what exactly your architecture is. If it is a ARM based x64 architecture, then of course RISC is there. Okay, and also there are some real world examples where CISC is still there. It is not that CISC is gone. CISC, I'd say it is still there. So uh, like if we have to run something like COBOL, Fortran, or those legacy C++ applications which are being compiled in x86, so C++ compiled in x86, we anyway have to run it in the CISC. Okay, so like Red Hat OpenShift, even like a little older version of the Microsoft SQL Server, on it is running on the Intel on the AMD hardware of the x86. So in that case, the CISC architecture is required. So again, what are the actual internals of it? That is more on a hardware side. So we are not going into the hardware internals of it. Okay. Now we will do a very interesting exercise, like how Google search works behind the scene, and more importantly, how it uses every bit of CPU performance to serve the search query results super efficiently. Okay, so probably we all know the use case. I don't have to explain it to you, like serve trillions of uh, web queries. Okay, so it is like serving the trillions of web queries per year, and what it is doing is like in zero point 0.2 seconds on average, while indexing billions of web pages, if not trillions. I don't know what is the exact number now, how many pages it actually have indexed, billions of web pages. It keep on returning. This is the API latency. API latency whenever we are making a request. Okay. Now every search query is processed end to end. Okay, so there is a fetch that happens, there is a calculation that happens, and there is also a write back to the write back to the user when a request comes. So let's try to explore that thing one by one. So suppose here is a user is there. Okay, suppose this is one user, and what this user does is, so suppose he search something around maybe best laptops of 2025, something like that. Okay, best laptops of 2025. Now if we have to do it in a very basic level, like where we do not have a lot of idea about the memory hierarchy and everything, what engineer would do is he would at first just create a front end server or a API server, and in the disk we will have all our um, indexed page. So I'm not going into the details of the Google search index. Probably I think most of the engineer across the world at some point of time they read about it, like what how Google indexes their data, how the web crawling and everything happens behind the scene. And so this is basically the indexed DB. And what this API server would do is API server would go to this index DB and then would get data from here, and from there it will return the data to the user. So the problem with this approach is it is too slow. Like suppose again and again, there are 500 people is searching best laptop, something around this, like best laptop or best laptop now or best laptop 2025. All are pretty similar queries, right? And this system of ours currently doesn't have any caching layer or anything. So even if 200 people out of this writes this best laptop, then for the 200 people it will go to the index DB and it will return the result to the API server, and from the API server it will be returned to the user. So the first and foremost thing is, of course, any engineer would suggest it's let's introduce cache. Okay, so the first thing is that let's introduce the cache, and what would happen is from here we are going to hit instead of this two, I will just move them a little. So here a layer of cache we will create. Okay, so it can be something like Redis or the memcached, anything can be there. So what it will do is in this Redis, it will check. check for hit, that whether it is there in the cache or not. So now you understand, if you consider this thing as an OS, listen carefully over here. If you consider the whole thing as a single operating system, now what we have started doing is, we have, by our choice, have started putting things into the cache memory. So how exactly OS internally controls it? Now we, by our own choice, started putting things into the those cache. Okay. So for this case, it doesn't matter whether OS is optimizing anything for us. We are introducing our own cache. Okay. So this is how the operating system concepts are even getting translated into here. So again, this is not as simplistic as we are talking about, this cache hit or cache miss. If it is, for example, if it is a cache hit, then it will return from here. In case of cache miss, again, it will store into the cache, and from cache only it will get returned to from here to the API server and to the user. Okay. So now again, at the scale of Google, at the scale of Google, bringing all the data and hitting the database, bringing them into the cache and maintaining them is a problem, because user can keep on chaining query like this, that best laptop now, best laptop 225 something around this. Okay. So what Google does is, it generally pre-computes. It pre-computes all the best laptops, the best smartphone of 2025, because we all, sometime or other, whenever we want to buy our smartphone, we do a Google search only, like what exactly the best for smartphone on a range of X to Y, like suppose some monetary boundedness I want to give, like something around 20,000 to 50,000, or it can be more. So around that, all those very popular search query, what Google does is, Google generally pre-compute the popular search query results. Okay. So this is one of the very important aspects of the designing system by leveraging the operating system, that I am going to have my own query processor, and it is going to have its own pre-computed data. Okay. And also with this, another thing comes is the predictive auto suggestion. So suppose Google has this kind of data already saved. So suppose you are just searching by best smartphone, you will see that the auto suggestion will already coming around best smartphones, best smartphone 2025, or best smartphone, suppose you are in Hyderabad, best smartphone shops in Hyderabad, something like that. Okay. So all these are auto suggestion, and many other things like the advertisement and many things will comes in play. So what Google does is, this kind of auto suggestion blocks also, it keep on saving in its own server. So in a, like, very sub-millisecond latency, you will see all those auto suggestion, and this predictive auto suggestion will automatically be fetched from the server and will be returned to the users. Okay. So now the very important nuance around this concept is, you see the temporal locality, or the spatial locality, and also things like caching. What Google has done over there is, it has tried to determine which can be the nearby semantic results, and which can be like my most searched queries, and it is saving all these things into its server. So although uh, the this is where the concepts of the OS internal shines. Even if the operating system might not give us all the things out of the box, using those concepts like how internal memory works, which memory is the fastest one, and from which memory I can have a transient data, how the temporal and the spatial locality happens. By leveraging all those things, we can write our system which are scaled to the millions of the billions users across the globe. Okay, so in a system like this, all these things like ALU, suppose I am asking Google search to make some kind of a calculation. You all know, like even Google search we can use as a calculator. So at that case, ALU will come in play. Okay, like the character comparison or the hashing some tokens for lookup or even string length calculation, that ALU can do. And in our RAM or in our cache, what we can do is we can store our pre-computed answers for popular queries or nearby semantic queries. Like if somebody is searching by Messi or someone is searching by Lionel Messi, it doesn't matter, right? So understanding that if somebody has already searched by Lionel Messi and the next person is coming and searching Messi, it can actually store the it can actually return the last stored results. Okay, and so here is the RAM holds the pre-computed things, and what disk does is like the whole indexed DB, which like storing or which has indexed this billions of pages across the internet. So you can see all these things comes together in any system or any scale system across the world. You see this operating system internals, you will be able to you will be able to see with your eyes every single places. Okay, so now we will take up one operations, like how the fetch, decode, execute, write, everything happens together, and from there we will get the idea how CPU performs parallel operations as well. Okay, so what is vertical parallelism, horizontal parallelism, everything we will uh, come to a conclusion with this example. So suppose I have a very simple program. Okay, I'm not even writing any program right now. Suppose this is some kind of a program I have, and suppose after this I need to print it. Okay, so I have this addition of two numbers, and then I will be printing C. Okay, it is just an algorithm or a very pseudocode. Don't even think it is in some language I'm trying to write. So this code, what happens is this code then gets compiled into assembly or machine code. Okay, and from machine code what happens is this goes into user process virtual address or the VAS. Okay, the virtual address space of the users, it get loaded into memory. So when I say loaded means, suppose there is a .exe is there. Okay, so when I run that .exe, which is able to do this addition, simple addition, the program will come to our VAS. And here, one of the most important concepts of operating system that takes place after this, when this operation happens, that is what we wrote here: the fetch, decode, execute, and write. Okay. So when this operation happens, there are fetch, decode, and execute, and the write happens. So let's take a deeper look into it. So compiler translate these programs. When we are talking about the machine code, it is something like this. I will just copy paste it so that you don't have to see me writing. So move from R1 is one of the register. So when we are talking about the R, R's are nothing but memory registers here. Okay, they are memory registers. So what I'm telling is that in my R1 register, load the value of A, that is 2. Okay, in my R2 register, load the value of B, that is 3, and then add R3, R1, R2. That means in R3 you uh, put the value of R1 plus R2 and then store that results into another variable called C. So this memory of A and B and C will be already in the virtual address space. And so how this thing looks is, let me write it for further clarity. So suppose I have something around this. Okay, so I have variable A. Variable A is here. Sorry. So you see these virtual addresses. These are nothing but some memory address. Okay, so now the concepts of virtual address and physical address is already been discussed in the previous video. So the bottom line is this virtual address is being converted to physical address. So physical address is the actual place where this value 2 3 this variable values are residing. So what exactly happening over there? Let's take a uh, little bit of deeper look. Okay, so there is a program counter. Okay, so this program counter knows what will be my next instruction. So from this program counter, or the program counter holds my next instructions. So from this program counter, what would happen is my instruction will go into my instruction register. So suppose there is this instruction register is there, or IR. To save my time, I will just write it as IR. Okay, and this IR, then what it would do is there is a layer of MMU, or the memory management unit. This MMU is responsible for giving me all the physical addresses of a given virtual address. So suppose I have this virtual address, what it will do is it will go to the MMU and it will ask that tell me what is the virtual address, and after getting this virtual address it will load this value. Okay, so now after IR know that okay, this is my address, what it will do is it will directly go to the memory or the RAM or anything you can say. Okay, it will take this value into the memory. So what happens over there is values are loaded. Okay, so now values are loaded into the memory. So the same thing happens for A and B both. So now in this state, what is happening over there is if I have to write an intermediary thing, both A and B is in memory. Okay, now what happens is I get the instruction. Okay, let me write it in a more clear manner. It is the memory registers. Okay, memory registers. So now that I know, what I have to do is I need to do these things, that add in my instruction register. The next thing is that I have this add R3, R1, R2. So that means you take R1 and R2 and put the data into R3. Okay, so what would happen over there is it would decode this whole instructions. Okay, so suppose this instruction is in a different form and it will take all the operands and it will do that calculations over there. So who will do the calculation? This add R2 R3, this calculation is from the IR, it will be passed on to the level of ALU, or the arithmetic logical unit will come into play here. So this is the ALU layer. Okay, this is the ALU layer. So now you understand that both A and B are in memory, and I am just performing this operation right now, and this results whichever it gets, what happens is this results will be written back to again my memory. Okay, so again my memory register will hold this memory of the data of R3. So now what is the state? Now the state is that in this particular virtual address, the value of 5 will be stored. So I think you got the idea by now. What is happening is, initially in the program counter tells the next takes the next instruction to be executed. It passes on to the IR, or the instruction register. Instruction register knows about these virtual addresses. It takes the virtual address, and from MMU it gets the physical address. It gets the physical address, and after getting them, it stores all of them into the memory registers. And initially both A and B are in memory registers, and in this, after that, what happens is it is being passed on to the ALU by the IR again, because IR has the instruction to add them up. And after ALU add them up, what happens is C will be, like, I can write over here, like C will store 5. Okay, so this is in the memory. So initially R3 will store 5. Okay, so once the R3 stores 5, R3 will store this 5, and then we are going to return, or we are going to write it value to our actual physical address space or the virtual address space, where we are going to have the value stored, and the later part of the program can use that. Okay, so again, this part of writing into the virtual address space, for that we are going to talk to the MMU, and after talking to the MMU we get that, okay, this is the particular location where we are going to store our data, that is this 0x1008, and we are going to store our value 5 after that in the variable of C. So variable of C was already in the memory space with this given virtual address space. Okay, so I think now you get it. So if I have to just do the whole register and the ALU flow, it will look something around this. At initial level, we are in our register, we are storing the 2 and the 3. We are making this addition, and then at this stage what would happen is we will go to our memory address. Okay, we will go to our memory. The memory will be something like 0x1008, and there we are going to store 5. Okay, so I think this part is clear. And one more thing I want to mention over here is about the decode decoding of the instructions. So generally, when this kind of instruction comes, this kind of instruction comes in a raw binary encoded version. For example, it can be something like this. I will just write it here. So, so suppose what might happen is the instruction register that we get, it gets a binary decoded instruction. Okay, so it gets a binary decoded instruction of this 001, 00 whatever, and then the decoder circuit does the bit pattern matching. So here, uh, all this, when this addition is being happening in the ALU, you can understand this thing is being passed on to the ALU. This is being recognized as add, and then the source register, the destination registers, everything will be interpreted, and then the ALU gets to execute the instruction. So now, what exactly is a fetch, what exactly is the decode, and what exactly is a execute? Let's revisit in a full detail so that it totally stays in our brain. So in the fetch stage, what is happening? So here I will just move this thing a little part. In the fetch stage, what is happening there? So if you are talking about the fetch stage, instructions are fetched from memory at virtual address space. Okay, so here we see that the instructions are being fetched from the virtual address space, and then in the decode phase, the instruction is then decoded. So you got the idea, right? Like initially we probably got something like this. Okay, so when we get the fetch probably will have something like this. Then in the decode phase, what happens is it gives you the complete instruction, where the instruction would look like the decoder circuits comes, and the instruction would look like something like add all the details like move R1A, R1A, and whatnot, like whatever we have written over there. Yeah, I have already written. I am copy pasting. So it would be something like that. So this is the decoded version. So now you understand fetching is basically fetching. Fetch happens here, like from the program counter, we get the next instruction loaded into the instruction register, and then in the decoder, we get the whole instruction. Then after the decoder, this the whole decoded instruction is being passed on to ALU. Now ALU, now at this stage, if I mark this as 1, if I mark this as 2, and if I mark this as 3, in this stage, what happens is after fetch decode, now our ALU knows what is the operation intended, that it is an add operation, and where are my operands. Okay, like when I say operands, it is like in R1 and R2. Where are my operands and what is the operation that I want to perform? And then what we want to do is this R1 and R2, we are going to put, the ALU is going to do this perform this thing. This is being known as execute stage. Okay, so now you understand what is fetch, what is decode, and what is execute. And after execute, what happens is, if at all we have to write it back to a given memory address. So if we are writing back to memory address, that means this this phase is being known as the write back. Okay, so now the most important concepts of the memory hierarchy, like the fetch, decode, execute, and the write back, you can understand how it comes together. Okay, so during the execute, the actual execution of the instruction happens undoubtedly, but you understand probably why fetch and decode is also important. And end of the day, during the write back, what happens is, this diagram will be better for us to understand. So now uh, we have this user space code, okay, that move the value of R3 and to this virtual address location. Now we again go to MMU, and what we do is we have the VA to PA, that is the virtual address space to the actual physical address. It gets converted. So physical address means definitely it is in the RAM, and then we are writing back, writing the data back to the RAM, and here the whole write back is completed, and the result is now ready, and it is stored in a destination. So from the destination registers, it is being stored into a particular memory location in our RAM. If we have to write back to the memory, then always remember this part is very important, this MMU to RAM. So anytime we are doing any scratching, scratching around the memory surface, the MMU will come in play, and the MMU is the part which does the uh, virtual address to physical address conversion. Okay, so we as a programmer and the process that we are running operates entirely on the virtual address space. Okay, so just this is one of the important point. Whatever the program we as a programmer write operates on virtual address space. Okay, and eventually MMU, like whenever we want to write anything into our memories, then MMU will come in picture, and it will convert and keep on writing there. So uh, now if we look closely into this diagram of ours, okay, so we have this fetch, we have then this decoding part. Okay, we have fetch, we have decode, and then we have this execute here, and we also have the write back. So what happens, suppose in a certain cycle, suppose the execute is taking some time to get uh, executed. Okay, suppose execute is getting some time to get completed. So now my question is, will the next instruction waits? So what would happen to the next instruction? Will it be totally waiting? Will it not be able to even come to the fetch stage? So in this case, one of the very important concept comes in play, that is pipelining. So just to clarify our question once again, for any new or next instruction, will it wait for all the fetch, decode, execute and write back to complete before even getting started? Okay, so in this case, what happens is the important concept of pipelining comes in play. So once we discuss pipelining, you will understand how greatly CPU optimizes the whole the whole procedure of the whole process of instruction execution. Okay, so what happens over here is, if we look to a new instruction, uh, just understand one thing, that new instruction is being introduced in every clock cycle, and it begins in the fetch stage. This is one of the key statement we should remember. So every time a new every time a new clock cycle comes, okay, so all the CPUs, they have a definitive clock cycles measured. So suppose there is a clock cycle 1, in clock cycle 1 one instruction will be there, in clock cycle 2 another instruction will be there. Okay, so it is like instruction 1, here will be something like instruction 2, something will come. Okay, so new instruction is being introduced in every clock cycle, and it begins in the fetch stage. Okay, now Meanwhile, the other instructions are already flowing through the decode, execute, etc. So now the thing is like that. Instruction 1 is, suppose it is in the decode stage. The instruction 2, it is already sitting in the fetch stage. This is coming from the clock cycle 1, and this is the clock cycle 2. Okay. So what happens over there? A great thing happens, that there is no time. Our CPU is actual idle, because the moment, although I am doing the decoding or the execute stage of the previous instruction, but at the same time my the next instruction is already fetched, so it is already being freed. And suppose the next instruction has gone into the write back stage, so it can always come to the next instruction, that is the instruction 2, can always come to the decode stage or the execution stage at that point of time. And this overlapping ensures that no pipelining stage, no CPU or pipelining stage is actual ideal, or there is like it is very imperative for increasing throughput. The operating system is being designed in this way that there is no wait time at all. Okay. Or the wait time is a wrong statement to make. I would rather tell ki there is no idle time at all. Okay. So suppose another subtraction request. So this has been the add request, right? So suppose it is a subtraction request. Another subtraction request comes in the next clock cycle, and that time we already have our add operation in execute stage. That request will anyway be pipeline. So this is why you can see this thing. What is happening over there is, this is a kind of a vertical overlapping is happening. Okay. A vertical overlapping is happening over there. Okay. So now we see that there are things like multi-core systems are there, like when we were discussing about the GPU. So if we have multiple instruction and I have multiple cores, okay, so that is known as the actual parallel execution. This is kind of pipeline and the overlapping instruction. Now what happens for the parallel execution is, parallel execution we already discussed in the part of the GPU, that when we have multiple cores. Suppose there are 16 core, 24 core machines are there. Okay. So I can map every single of my instruction to those different cores. In that case, what will happen is, even there will not be that pipeline, the vertical slicing time will be there. Rather, what we are going to have is a true parallel execution. So if I have multiple instruction, I can use multiple cores, and that is known as the actual parallel execution. So each core does its FDE, or like, the if I talk about like abbreviation. So this, suppose this is happening in the core 1 in T0 time, and at the same T0 time this core 2 is happening at the same T0 time. Okay. So the advantage is, this cannot happen for the pipelining. In pipelining, what will happen is, suppose I have this core 3, it is happening again in the T0 time. In the pipelining, this one will happen in T0, the second one has to happen in T1 or T2. Okay. So if I just write it again, core is a wrong thing to mention here. If the I can say the first instruction is the second instruction and this is the third instruction. So they will happen in different timeline for sure. If it is happening in T0, this will happening in T1 and this will happening in T2, because in a same because in the same core two um, two execute operations cannot happen in the same time. Okay, so now parallelism, as we understand, this parallel execution is nothing but on a hardware level we have multiple cores and a multiple ALU, and also from the software level there is something called CPU pinning, which we have already discussed in one of our previous operating system and as well as in our system design videos. uh, Through this CPU pinning we can from the software level we can handle like in which core we we could actually do go, and also in the OS level there are some concepts of the context switching and the other things that comes to aid the parallel execution. So on this regard, we have already discussed what context switch is. Okay, but still we will just touch upon the concepts here once again to make sure that we understand how context switch comes with the parallel execution pipelining and all the other things. Okay, so on a very high level, what OS does is, like, suppose there is a particular thread is going on. Okay, some thread execution is going on. What OS does is OS saves context of the current thread. Okay, what it does is it does the PC registers, etc., etc. The moment like some interrupt comes in and when an interrupt comes in. So what exactly interrupts? I think you, if you know, interrupt means some kind of a operation. Suppose I am taking a CPU memory. Suddenly I know that I have to wait for the IO, or I am waiting for the database results to come back. So in that case, there is no point of making that particular piece of system idle, right? Our CPU core idle. So at that point of time, what it does is it will what operating system does is it saves all the current threads into control block, and OS restores another thread's context to execute. Okay, now let's understand this concepts a little um, detailed manner with the FDE cycle. Okay, suppose there is a slow instruction is going on. Do you think if there is a slow instruction is going on or some slow execution is going on, the context switch will play? So my question is, for a slow instruction in execute cycle, suppose, okay, do you think context switch will happen? The answer is no. There is a very prevalent misconception that if something is in taking a little more time, the context switch might be happening. No, that is not the case. Okay, so whenever a slow instruction happens, uh, context switch doesn't happen. But suppose my instruction is waiting for IO. Okay, suppose my instruction is waiting for some kind of a IO operation, and our CPU is completely becoming idle because the IO, the database results, or some kind of network operations are going on. Okay, so at that point of time, the context switch does happen. Okay, so here the answer is yes, and here the answer is no. Also, please note the context switch happens when the time slice may expire. So, suppose a thread is being given a certain FDE cycle, okay, and it wants to do some 15 FDE cycle, and it does not interrupt the individual instruction. Okay, so suppose a thread is doing like thread is doing 15 FDE cycle, it has to go through, and after 10 FDE, suppose time slice is over. Only after that FDE stage, then only like it will be saved into the control block, and the next thread context will be loaded to execute. So remember, in between a single instruction, time slice never interrupts, because that will be a very difficult situation to handle. Okay, like suppose you are in the decode stage and you are just making it vanish from the memory, that will not happen. So if a thread runs too long, measured in time slice, suppose 5 millisecond, the OS scheduler preempts it. It triggers a context switch. It gives CPU time, that CPU time to another thread, and when the CPU time is again free, then this thread comes back. Also, context switch happens when the time slice may expire, and context switch happens when a IO wait might happen. Okay, so you cannot interrupt an instruction of a mid FDE cycle. Okay, instruction must run atomically. This fetch, decode, execute, and the write back has to done in a complete manner. It might happen that if 15 instructions are there, okay, 10 instruction or 11 instruction is completed, and during the 12 the state is being saved, and another thing comes in because of the time slice expires. So this OS can preempt the thread anytime, even during the instruction execution. Okay, but the hardware will wait for the current instruction to complete for sure. So I hope you understand what preempting means. Like that I do not want like the current thread to execute. Rather, I want my own thread to execute because the time slice is over. So that is the concept of, again, the CPU scheduling. So all these things, CPU scheduling, fetch, decode, execute, probably you can understand that everything comes in a full cycle over there, over here. And now probably also you understand now, when you see like in your practical life, okay, in your laptop, suppose your laptop is hanging for some time. Okay, your laptop is hanging, or what we say is completely freezed. Now we kind of understand why it is happening, right? Because probably the instruction that you have given, uh, it is unable to come into the execute cycle because it is currently opening, maybe in the fetch or maybe into some other stage, because the number of cores or the number of cache or the number of RAM you have, which is not enough for this. So not only the RAM is important, probably you understand RAM is only one part of the system, but if the processor has multiple cores and a more powerful clock cycle management, then your laptop will definitely will not go into the freeze mode. And also you probably understand how GPU does the parallelism, because we have those thousands of cores, and it is able to execute simple instructions. So one by one, all the matrix multiplication and everything, it keep on putting into the parallel uh, parallel execution. And if at all something is not free, because those are like simple instruction anyway, like the matrix multiplication and everything that is going on, we can just pipeline our instruction. So probably it like if you are like, after this video, if you are able to answer those practical scenarios, like why GPUs are preferred for scenarios like LLM, or when exactly my machine is getting freezed. Why? By killing some of the processes in the task manager, make it unfreeze. Probably then you got the idea around it. So that's the video, guys. Like, if you have made till this far, I am sure you have learned number of things. Please put any questions you have in the comment section. I will try my level best to answer them. So see you in my next video, and that will be the last part of our OS internals. It will be on the socket management, where operating system and the networking will come in together, and we will see how the like when a request comes into from a remote server comes into our operating system, how it is being handled. So till then, uh, all the best. See you in my next video.